So let's look at some examples of simple zeros. In a sense, any function you can think of, if it's a simple function of just one elementary function, the zeros of that function are going to be simple. I can't think of any examples where they're not simple. Of course, you can verify it by differentiating, but in practice it's just not necessary. You can just say that they're simple. It's not really necessary to show it every time. But yeah, some examples. Sine Z, well, you can think of sine. I mean, the way you picture it is the fact that when you've got a zero sine, I know this, I'm drawing the real function, obviously, the gradient at the zeros is not zero. That tells you immediately that it's a simple zero. Okay, so sine has zeros at n pi. Cos is shifted sine, that has zeros at n plus a half pi. Now, sine and cosh, we've said, are like sine and cos, except you multiply everything by I. So the simple zeros at sine and cosh are the same as for sine and cos, but multiplied by I. Here, we can't really draw a graph so easily, but if you like, you can differentiate sine and get cosh and realize that cosh of n pi I, of course, is cos of n pi, which is plus or minus 1, or minus 1 to the power n. Similarly, cosh, if you differentiate cosh, you get sine, and sine of n plus a half pi is never 0. Tan of z, well, you get tan by dividing sine by cos, and if sine has a simple 0 and cos doesn't have a simple 0 at n pi, then tan also has a simple 0 at n pi. In this example, z to the 4 minus 1, well, this obviously has, the way to think about this one is that we can factor it. So z to the 4 minus 1 is simply z plus 1 times z minus 1 times z plus I times z minus I. So obviously z equals plus or minus 1 or z equals plus or minus I give us 0. But now we're thinking of the definition z minus z naught to the m times g of z. And obviously this g is the remaining term. So for example, if z naught is 1, then g would be all of this stuff, which is definitely not 0 when z equals 1. So you have simple zeros at all of the roots of this polynomial here. And finally, if we multiply two functions which have simple zeros at different places, so sine and cos, all of these simple zeros are at different places, then this function combined will have simple zeros at n pi and at n plus a half pi. So overall that's n pi by 2, which is also obvious if you rewrite sine cos as half sine 2z.